It's no secret that there's a water crisis in California. This problem has been percolating for decades. There's a reason no solution has been implemented. I want to share with you why the water issue has been ignored and have some good news to share. There's a solution. Here's why the water issue has not been addressed. There's been a battle between environmental interests, agricultural interests, and municipal interests. Here's a quick synopsis of each party's focus. Environmentalists want to protect the fish. Farmers need water for their crops. Municipalities need water for people. There's a bold new plan that addresses all of these needs. The Los Angeles Desalination Project will generate new water, won't harm fish, and won't increase the load on the grid. Let's take a look at the details of this new plan.
Welcome to the Los Angeles Desalination Project presentation, a sustainable solution to the California water crisis. This presentation will cover 3 topics. First, we're going to identify California's major conveyance systems. Then we're going to compare conveyance and desalination energy costs. And finally, we're going to talk about why the Los Angeles Desalination Project is the most sustainable solution. In order to understand the necessity for the Los Angeles Desalination Project, it's helpful to understand how the current water conveyance system works. California's water supply is complex, and the water comes from various sources. We're only going to touch on the largest aqueducts and canals in California. One place where California receives water from is the All-American Canal, and you can see that in the bottom right-hand side of this slide. The water comes from the Colorado River and is used by agriculture. It is the largest irrigation canal in the world. It's owned by the U.S. Bureau of Reclamation and operated by the Imperial Irrigation District. Now let's talk about the Colorado River Aqueduct. This aqueduct delivers water from the Colorado River to urban users in Los Angeles. It is owned and operated by the Metropolitan Water District of Southern California. The Los Angeles Aqueduct delivers water from the Owens Valley to urban users in Los Angeles. It is owned and operated by the Los Angeles Department of Water and Power. The Delta-Mendota Canal provides water from the Delta for Central Valley agriculture and is part of the Central Valley Project. The California Aqueduct also provides water from the Delta. The consumer of this water are urban customers in the Central Valley as well as Southern California. It is owned and operated by the California Department of Water Resources. The Sacramento-San Joaquin Delta, also commonly known as the Delta, is the hub of the California water system. About 80% of the water entering the Delta is from the Sacramento River, and about 20% of it is from the San Joaquin River. However, much of the San Joaquin River is diverted into the Friant-Kern Canal prior to reaching the Delta. The Friant-Kern Canal serves Central Valley agriculture and is also part of the federally funded Central Valley Project. Now let's see why the Delta plays such a big role in California water today. The Delta is the main source of California's water, with 2/3 of California's water coming from the north and 2/3 of California's population living in the southern part of the state. This is an overview of the pumping plants in the Delta. The Clifton Court Forebay is a large reservoir at the southern tip of the Delta where the Tracy Pumping Plant and the Banks Pumping Plant export Delta water south. Pumping water at the Clifton Court Forebay is known to be harmful to fish. One idea said to protect fish is to connect the Sacramento River and the Clifton Court Forebay with 2 30-mile-long Delta tunnels. However, people from Northern California consider this a theft of their water. This proposal was defeated in 1982 when it was called the Peripheral Canal Act. Environmentalists assert overpumping is the greatest threat to fish and wildlife, and the Delta tunnels will only make the problem worse. The Banks Pumping Plant supplies the California Aqueduct. The California Aqueduct is the longest conveyor of the state water project. At over 500 miles in length, it conveys water from the Clifton Court forebay to as far south as San Diego. Over the years, several branches have been added to expand its reach. However, expanding conveyance does not increase the overall water supply. The Tracy Pumping Plant supplies the Delta Mendota Canal. This agricultural water is part of the Central Valley Project. California is the nation's #1 farm state, and these federal projects feed America. If less Delta water was sent to Southern California for urban use, then more Delta water could stay in the Central Valley for farming. Population growth is exhausting the Delta's water supply, and the best place to invest in new water is Southern California. We're now going to move from looking at the pumping plants at the Delta to the 4 key California aqueduct pumping plants. These are the 4 California aqueduct pumping plants that could free up the most energy if Southern California received more of its water from the sea than from the Delta. The Tehachapi Mountains form the southern border of the Central Valley. The energy required to pump water over the Tehachapi Mountains is staggering. These 4 pumping plants have a combined capacity of 1,300 megawatts. That's equal to 1 nuclear power plant or 3 coal-fired power plants. 56% of all California aqueduct water is pumped over the Tehachapi Mountains into Southern California. That is also 25% of all water pumped from the Clifton Court forebay. If Southern California stopped using Delta water, then that water could stay in the Central Valley for farming, and the energy from these 4 plants could instead be used in LA for desalination. These 4 plants account for 89% of the total energy required to convey water from the Clifton Court forebay to LA. Edmonston accounts for 59% all by itself. High energy costs and the Delta's limited water supply are the primary reasons why the era of expanding conveyance needs to end. The A.D. Edmonston pumping plant is the world's highest lift. The vertical distance between the intakes and the outlets is nearly 2,000 feet. The plant capacity is 2 billion gallons per day. Edmonston's average flow in 2010 was 1.34 billion gallons per day. It would take at least that amount of new water in LA to make Southern California independent from Delta water. The LA Desalination Project proposes a startup capacity of 1 billion gallons per day and a build-out capacity of 2 billion gallons per day. In the next set of slides, you'll get to see how conveyance and desalination energy costs are virtually identical in Southern California. The California Aqueduct is part of the State Water Project. Each time that water passes through a pumping plant, it adds to the total energy cost. Most of these pumping plants have an energy per volume, known as E/V, between 0.3 and 0.6 megawatt hours per acre foot. The Edmonston plant is 2.26 megawatt hours per acre foot. Edmonston is the energy equalizer between conveyance and desalination in Southern California. The California Aqueduct currently requires 3.81 megawatt hours per acre foot to convey water from the Clifton Court forebay to Los Angeles. If the Delta tunnels were to be built, that would increase to 4.11 megawatt hours per acre foot. Let's compare this to desalination. The estimates of the energy per volume of the Los Angeles Desalination Project are shown in the lower right corner. A 100% electric desal plant will have an energy per volume of 4.21 megawatt hours per acre foot. However, when renewable pumping is added, the energy per volume drops to only 3.81 megawatt hours per acre foot, the same as conveyance. Renewable pumping will generate 188 million gallons per day without electricity. This is referred to as the free water. Anything over 188 million gallons per day will require electric water. In this example, a 2 billion gallons per day plant will have 188 million gallons per day of free water and 1,812 million gallons per day of electric water. The Sorek plant in Israel is currently the world's largest reverse osmosis desalination plant at 165 million gallons per day. The Los Angeles Desalination Project free water alone would break this record. 2 billion gallons per day? That would destroy it. Let's review the water systems in Southern California. The Colorado River Aqueduct conveys water from the Colorado River to LA. Its energy per volume is 2 megawatt hours per acre foot. This is about half the cost of the California Aqueduct. However, the 7-state quantitative settlement agreement prevents California from increasing its pumping from the Colorado River. The All-American Canal takes water from the Colorado River for agriculture. This is yet another example of cities and farmers fighting over the same water. Water scarcity is both a state and a federal issue. We need to work together to solve this problem. The Los Angeles Aqueduct delivers water from the Owens Valley to Sylmar by gravity. The Los Angeles Aqueduct is actually 2 aqueducts. The first aqueduct is between Mono Lake and Sylmar. It is 233 miles long and it's over 100 years old. The second aqueduct is between the Highway Reservoir and Sylmar. It's 137 miles long and is 50 years old. This aqueduct was built in great haste to prevent a loss of water rights for LA. Because of this lack of planning, it has virtually no hydropower. Between the aging infrastructure of the first aqueduct and the lack of hydropower on the second aqueduct, it's time to replace the Los Angeles Aqueduct with the Los Angeles Superconduit. This will maximize renewable energy production and dedicate all of it to desalination. Let's zoom in to take a closer look at the water systems in LA. These 4 California aqueduct pumping plants consume 1,000 megawatts only 70 miles outside of LA. Using that 1,000 megawatts in Sylmar to generate 1,812 million gallons per day of electric water would be a much wiser choice. This would offset all Delta exports to LA at net zero grid impact. Sylmar is the ideal location for a 2 billion gallons per day underground desalination facility because of existing infrastructure, such as treatment plants. The Joseph Jensen Treatment Plant, 750 million gallons per day, and the Los Angeles Filtration Plant, 600 million gallons per day, are both in Sylmar. Another existing infrastructure at Sylmar is water storage. Upgrades to the Newhall Tunnel and the California Aqueduct's West Branch would allow Castaic Lake and Pyramid Lake to store and distribute new water to all of Southern California. The final piece that makes Sylmar ideal is the Pacific Intertie. This Bonneville Power Administration DC power line terminates in Sylmar. There's protection from the sea. Sylmar has an elevation of 1,200 feet and is 20 miles from the coast. 100 years of anticipated sea level rise will have no harmful impact to the facility. There's also renewable energy. Replacing the Los Angeles Aqueduct with the Los Angeles Superconduit will give the new facility a renewable energy power supply. Let's see why the new Los Angeles Superconduit will produce more renewable energy than the existing system. This diagram is a rendering of what the LA system might look like. At the top of the diagram is the Highway Reservoir. This water is transferred to the LA Superconduit. The LA Superconduit is a continuous and unbroken pipeline that delivers water to the Sylmar underground facility at a very high pressure. The power that can be derived from the act of falling water is equal to the flow times the fall. Although the flow is dependent on annual precipitation in the mountains and is relatively constant, the fall can be increased and therefore the power. Doing this will take full advantage of the 2,500-foot elevation difference between Highway Reservoir and Sylmar. The current Los Angeles Aqueduct has much of its water falling without generating power. As you can see from the rendering, various reservoir elevations are noted, and water and energy flows are displayed. Building the Los Angeles Superconduit and the Sylmar underground facility will allow LA to become less dependent on water from the Delta and use its energy more wisely. Next, let's look at how water-to-water energy conversion is more efficient than using hydroelectric energy for pumping. This slide has 3 reservoirs and is the most basic form of water-to-water energy conversion. Water-to-water energy conversion is basically hydropower without electricity. The upper reservoir in the center is the final destination for the other two reservoirs. Water is collected in the mountain reservoir and is allowed to fall to the upper reservoir through a water engine. The fall is the elevation difference between the mountain reservoir and the upper reservoir. The lower reservoir is below the upper reservoir, so it must be sent through a water pump. The rise is the elevation difference between the lower reservoir and the upper reservoir. The combination of a water engine and a water pump is called a water engine pump, shown at the bottom of the slide. The energy balance requires that the mountain reservoir flow times the fall equals the lower reservoir flow times the rise. This may also be referred to as renewable pumping. All renewable pumping will be done within the Sylmar underground facility. Since the demand for pumping in Sylmar will never end, generating electricity would be considered extremely wasteful. When used for desalination, the lower reservoir is represented by the sea. However, this makes the system more complex, since salt must be removed prior to it being lifted to the upper reservoir. Let's examine how this technology can be expanded to be used for desalination. The Sylmar underground facility will be dug from a surface elevation of 1,200 feet to a depth of 100 feet below sea level. The facility will have limited horizontal space, but almost unlimited vertical space. The stacked units are a series of power and pumping machines all stacked on top of each other, sharing a common drive shaft. Let me briefly explain the function of each machine and how water travels through the system. The seawater pump draws seawater from the seawater reservoir and forces it through the membrane bank. Two liquids exit the membrane bank, the brine and the fresh water. Typically, this is a 50-50 ratio. The brine engine recovers energy from the brine before it is discharged into the brine conduit. The freshwater pump lifts the newly generated fresh water to the surface for treatment. The stacked units will include a motor gen to receive electrical power from the Pacific intertie. The stacked units will also include a freshwater engine to receive renewable energy from the new Los Angeles superconduit. The freshwater engine will provide reliable power even in the event of grid failure. Multiple stacked units and multiple membrane banks will give the system redundancy. Let's look at the conduits that will be needed to bring water to and from the Sylmar underground facility. 4 superconduits will travel 137 miles from the highway reservoir to Sylmar. The first 110 miles will be installed using trenches. 2 San Andreas fault crossing structures will protect the superconduits from seismic activity. This will also be the transition point from trenches to tunnels. The 4 superconduits will be placed inside 2 line tunnels for the last 27 miles, 2 conduits per tunnel. 3 types of conduits will intersect the Sylmar underground facility at different elevations. The superconduits will deliver Owens Valley water and renewable energy to the facility. The coastal conduit will deliver seawater to the bottom of the facility. The brine conduit will take brine away from the facility. All conduits within Los Angeles will be located deep underground. Tunnel boring machines will dig 4 tunnels. 2 superconduit tunnels, 1 coastal conduit tunnel, and 1 brine conduit tunnel. Beach wells near Tobango Beach will prevent marine life and other debris from entering the coastal conduit. Using the sand and earth as a seawater pre-filter will reduce operating costs. The coastal conduit will deliver seawater to Sylmar. The brine conduit will take brine from Sylmar to Long Beach. Miles of separation between Topanga Beach and Long Beach will prevent brine water from being recycled. The drop pits will aid in the deployment and retrieval of the tunnel boring machines.
Here's a summary of the key points of the Los Angeles Desalination Project. Reducing Delta water exports to Southern California will give Central Valley farmers 25% more water and save 1,000 megawatts of power. This power will then be used in Sylmar to generate up to 1,812 million gallons per day of electric water at net zero grid impact. Building the new Los Angeles superconduit will generate 188 million gallons per day of free water in Sylmar, independent from the electric grid. The Sylmar underground facility will tie into existing infrastructure to treat and distribute new water to all of Southern California. The Los Angeles Desalination Project will be the largest reverse osmosis desalination plant in the world. Bold action is needed to avoid escalating conflict over water and uncontrolled food inflation. Thank you for your interest in the Los Angeles Desalination Project. You can visit our website, bellamachines.com, to see some commonly asked questions and answers, as well as the project proposal in full and the project feasibility study plan. Thank you so much for your interest in the Los Angeles Desalination Project.